All right, let's talk about one of the biggest challenges in all of machine learning. The goal is always, to build a model that's not too simple, not too complex, but is, just right. It really is a classic Goldilocks problem. And when you get it wrong, well, things can fail in some pretty spectacular ways.
And it all starts with this kind of weird, paradoxical question. How is it even possible for a machine to learn too well? I mean, that sounds like a good thing, right? But believe it or not, this idea is at the absolute heart of a huge hurdle that every data scientist has to overcome.
So, to really get our heads around this, let's use an analogy we can all relate to. Picture two students getting ready for a huge final exam. First, you've got the slacker. You know this person. They barely crack open the textbook. Then you've got the crammer. This student memorizes everything, every word, every diagram, even the coffee stains on page 82. But here's the kicker. Despite their totally opposite approaches, they both get the same result. They both completely bomb the final exam. This exact paradox plays out all the time with machine learning models.
Okay, let's start with our first student, the slacker. In the machine learning world, this is a perfect stand-in for a problem we call underfitting. Underfitting is basically when a model is just, it's too simple. It hasn't learned enough from its study material, what we call the training data, to actually grasp the important patterns. So just like our slacker, it does terribly on the practice questions, and then, no surprise, it completely fails the final exam when it sees problems it's never encountered before. It just didn't learn the material. Simple as that. Now, let's swing to the total opposite end of the spectrum and look at our second student, the crammer. This is where we get into the much more sneaky and frankly more common problem of overfitting.
See, overfitting is what happens when a model gets a little too smart for its own good. It doesn't just learn the underlying patterns, it literally memorizes the training data itself, and that includes all the random noise, the flukes, the irrelevant details. It's our crammer student who can recite the textbook word for word but has zero actual understanding of the subject. The model absolutely crushes the practice questions, but then it's totally useless when it faces new data on the final exam.
And this example just nails it. Imagine you're training a model to recognize dogs. But what if almost all of your training pictures show dogs playing in grassy parks? The model might make a bad connection and learn that green grass is a key feature of dog. So what happens when you show it a picture of a dog sleeping on a rug inside a living room? It gets confused. It fails. It didn't learn what a dog is. It just memorized the context it was used to seeing.
So, if these are the two big ways a model can fail, how do data scientists actually figure out which problem they're dealing with? Turns out, it's all about comparing performance on the practice test versus the final exam.
The diagnosis really comes down to this. You look at how the model did on its homework and compare it to the real test. If it performs poorly on both, you've got a slacker. That's underfitting, or what's called high bias. If it gets a perfect score on the training data, but then fails the evaluation, you've got a crammer. That's overfitting, or high variance. But if it does pretty well on both, now you've found the sweet spot. That's our ideal student, the scholar. But wait a second, there's a catch. If you use up all your new, unseen data just to test the model, you have nothing left to actually use it on in the real world. It's like using the final exam just for practice. So, how can you get a trustworthy score without cheating and peeking at the answers? Well, there's a really clever solution called k-fold cross-validation. Instead of having just one big final exam, you give the model a bunch of smaller pop quizzes. You basically split your study material into, say, 5 chunks. You train the model on 4 of those chunks and test it on the one it hasn't seen. Then you repeat that process until every single chunk has been used as a test. By averaging the scores from all these mini-tests, you get a much more reliable idea of how the model will actually perform when it matters.
Okay, so you've done your tests and you've confirmed it. Your model is a total crammer. What do? Just throw it away and start over? Nope. Thankfully, there's a whole toolkit of techniques designed to fix overfitting. It's all about teaching a model how to truly learn and generalize instead of just memorizing.
First things first, you can give it better study materials. Honestly, the #1 best way to fight overfitting is often just to get more data, more varied and diverse examples. But if that's not an option, you can use something called data augmentation. This is where you take your existing data and make small changes, like flipping an image, rotating it a bit, or zooming in, to create brand new examples for the model to learn from.
Next up, you can teach the model smarter study habits. One popular method is called early stopping, and it's pretty much what it sounds like. You watch the model as it's training, and you stop the process right at that sweet spot, just before it tips over from learning patterns into memorizing noise. Another technique is pruning, where you help the model focus by removing information that isn't important. It's like telling our student, hey, don't worry about the page numbers or the publisher's logo, focus on the actual concepts. We can also help the model avoid distractions with a technique called regularization. Think of this like adding a penalty for being too complex. The model gets fined for paying too much attention to features that aren't that important. This forces it to focus only on the signals that really, truly matter for making a good prediction and to ignore all the distracting noise.
And finally, one of my favorites, the group study method. This is known as ensembling. The idea here is that instead of trying to build one single genius model, you train a bunch of different simpler models. We call them weak learners. Any single one of them might not be that great on its own. But when you combine all of their predictions together, the collective wisdom of the group is often way more accurate and reliable than any single genius model could ever be.
So when you pull all this together, you see that building a great machine learning model isn't about getting 100% on the practice test. It's all about finding that delicate balance, that Goldilocks zone, where the model has learned enough to be useful, but not so much that it's forgotten how to think for itself.
And it all comes down to this. On one side, you have high bias. That's underfitting. That's our slacker model. That's way too simple. On the other side, you have high variance. That's overfitting. Our crammer model that's way too complex and has just memorized everything. The entire job of a data scientist is to carefully navigate between these two extremes to land right in that sweet spot and build a model that performs well, not just on the data it's already seen, but on all the new messy data it's going to face out in the real world.
And that really leaves us with one last big question to think about. This whole challenge forces us to ask something fundamental about learning itself, whether we're talking about a computer or our own brains. What's the real goal? Is it to have a perfect, flawless memory? Or is it to achieve true understanding?